This is 5.3, mean and variance of a discrete probability distribution. In order to decide between alternatives in math class, business, wagering situations, etc., we use a mathematical methodology. This methodology involves finding the mean, variance, and standard deviation of a probability distribution. So this is what people actually do. Businesses hire stats. They look at the probabilities, the outcomes, and stuff. Obviously, it's a little more complicated probabilities than what we're looking into, but the ideas are the same. They kind of look at, okay, what's the most likely option, and then look at the variance and standard deviation of things to see. Notice that all of these are actually population. Okay, we're not dealing with any samples right now, so it's population mean. It is a population variance, and it is a population standard deviation. It has to be. If it's not, it is not a probability distribution, because a probability distribution has all outcomes, and a population deals with all pieces. So if we took a sample, we wouldn't be using all the outcomes, meaning we don't have a probability distribution. Okay, so that's one thing to keep in mind. Everything is a population value. So we have three equations basically. So I'll highlight in three different colors. The first is we take x times p of x and add them all up, and that will give us our mean. The second little extra piece here, so you have x squared times p of x and add them all up, and then after you do that, then you subtract whatever you got for your mean squared. Okay? And the last one is the standard deviation, which is still the exact same formula as it has always been, the square root of variance. Okay, start recognizing these things. You need to know that mu is the population mean, sigma squared is the population variance, and sigma is the population standard deviation. As soon as you see those variables, they should trigger something in your mind so that you remember. Okay, so we need to fill out our thing here. So x, p of x, that means we take the x times p of x. So that's 0. 0 times 0.5 is 0. 1 times 0.5 is 0.5. X squared, so we square each x value. So you get 0 squared is 0. 1 squared is 1. Happens to be the same. And then x squared p of x. So x squared times p of x, and you get 0 and 0.5. Not a very exciting thing. We're talking about flipping a coins and getting tails. Right? Because 1, the one we want, is tails. 0, the one we don't want, is heads. Okay? And so it's not super exciting. We need sums. So if I add up this column, I'll use a different color to recognize that this is the sum. The sum of x p of x is, add them up, 0.5. And finally, the sum of x squared p of x is, add them up, and you get also 0.5. Okay, one thing to recognize that the mean is the same as the expected value. Okay, so if I ask, what is your expected value? That is our mean. Okay, the one we expect to happen is the mean value. So keep that in mind. It doesn't have to be one of these x values, right? The mean can be a decimal, the expected value can be a decimal, saying, well, it's between these two, and based on the value, we expect 1. Okay, well, think about a coin flip. If I flipped a coin, what do we expect? Well, we expect half the time it's tails, half the times it's heads. And if we look at our equation, which for the mean is the sum of x times p of x, which is right here. We already found that. The answer is 0.5. And that makes sense. It's halfway between heads and tails. We expect it to be half the time heads, half the time tails. So that's why that is our expected value. The variance, okay, so this one has a little bit more involved. So I have sum of x squared p times p of x, which we already found is 0.5, minus the mean squared. A lot of people forget that step. Okay, so let's actually calculate it now. So I have 0.5 sum of x squared p of x, right here, 0.5, minus the mean squared. So use your calculator, mean squared. So in this case, it's 0.5 squared, because that's what we got for our mean squared. Type that in, and you get your answer of 0.25. So that's my variance. And the last equation is the square root of the answer we got for the variance. That will give us our standard deviation. So square root of 0.25, and I get, it's not super exciting, but I get 0.5. And there it is. Done. Okay, so let's look at a little more exciting version of this, I guess. So we don't have just 2 options. Now we have 1, 2, 3, 4 options. So x is 2, 4, 6, or 8. P of x is 0.4, 0.3, 0.2, and 0.1. So as the x value gets bigger, the probability that it will occur gets smaller. Okay, and so we have to take that into account, right? When we find our mean, we're going to expect it's going to be closer to the 2 or the 4 and further away from the 6 and the 8, right? Because these things are more likely to occur, so the expected value is going to be closer to those 2. So x times p of x for each one. Use your calculator if you should be using your calculator. Okay. Then I get x squared, which is 4, 16, 36, 64. Then we get x squared times p of x. Okay. And then we get our sums. So the sum of x p of x, if I add it all up, is 4, which should tell you something. And the sum of this one is 20. Okay, so we get our mean. The mean is the sum of x squared p of x, so the answer is 4. The expected value is a 4. That, based on these, is the one we expect out of this on average. Okay, so take into account the one that's most likely to occur is a 2. That's not what expected value is. The one that most likely is to occur is 2. A mean is the average, right? So the expected value is the average of all of our results. The average number in all of our results is a 4 because the 2 and the 4 are more likely than the 6 and the 8. So these are going to take more into account, basically. And so that's why it's closer to that end. That's why our expected value is closer to that end. If we took the average of all of our results, we expect to get a 4. The variance, you take the sum of x squared p of x, which is 20, minus the mean squared, don't forget that. And I also get 4. It's coincidence. And then this one is the square root of the variance, which is 2. So there we have it. My mean is 4, my variance is 4, my standard deviation is 2. Remember, standard deviation is how spread out the data is. Okay, so if you look at this one, 0 and 1, 0.5, it's a really small standard deviation. Those are pretty close together. A 2, it's still a decently small standard deviation, but not as small, because you can notice our data is more spread out. It's going from 2 to 8 now. So it's a little more spread out, so it makes sense to have a higher standard deviation. Okay, now we have a probability function to use. So you have to understand how to plug in and how to get your probability out. So it's not quite as simple as before. So we actually have another column to fill in, which is the probability. So for 0, I plug in 0, and I get 0 probability. So that's interesting. A 0 has no chance of occurring, even though it's one of the values they gave us. I'm not going to use it. Notice the hint. Use fractions. If they give you a probability function with fractions, it's usually easier to use fractions. So the next one is 1/6. The one after that is 2/6, which we can simplify if you want, but I would recommend not. We don't need to. Our final answer we need to. I'm going to leave it as 2/6. 3/6, once again, it can simplify, but I'm not. I'm going to leave it as that. You'll see why in just a second. Okay, so we multiply. So I get 0, 1/6. 2 times 2/6 is 4/6. You only multiply, since it's a whole number, you only multiply the top. 3 times 3/6 is 9/6. And notice we have a common denominator now. So if I add all of these up to find my sum, which this is one of the sums I need, I get 1 plus 4 plus 9, which is 14. And the denominator stays the same, common denominator. we will have to simplify or use a decimal when we get to our answer. But don't make things harder. Use common denominator they gave you already of 6. So I square each one, 0, 1, 4, and 9. X squared times phi of x. So that's still 0. All of these are 0 because they just can't occur. This one is still 1/6. This one is 8/6. And this one is 27/6. Okay. So we get that sum. And once again, if we were nice to ourselves, kept the common denominator, it's easy. 1 plus 8 is 9, plus 27 is 36/6. Okay. So now we actually have to do a little work here. This one I could just type in 14/6, and I get 2.33. Our expected value is 2.33. Notice as we're getting bigger, the probability is also getting bigger. So that's why the average value that we are going to get out of this situation is in between the 2 and the 3. Okay, so it makes sense. Variance. This column, which is 36/6, minus the mean squared. So I'm just going to use the exact value here, just to make things a little easier. Type that into my calculator, and I get 0.56. Right, this we use to calculate that, so that's why I just used it for the mean, because it's the exact. And then I take the square root of that. And you get your standard deviation. Notice the smaller standard deviation again, it's bigger than the first one, because instead of just 0 and 1, we have 1, 2, 0, 1, 2, and 3. But it's still a small standard deviation, because these are all very close together in the end. Okay? So that's how you calculate mean, variance, and standard deviation of probability distributions. Now we're going to use that in one question. So we actually have an actual situation we can look at. So we're going to look at games of chance and if they are fair or not. Which, if you found the odds of like a poker game or blackjack or slot machine or any of the other things, roulette, craps, whatever you're actually betting on at like a casino or something like that, places that have games of chance, if you found every outcome and their probability, you could do this test and you'll find that none of them are a fair game. Okay, that's the whole point, right? The reason casinos stay in business is they don't give you fair games. If they gave you fair games, they would lose too much money because they would come out even every time. That's what makes it a fair game. So evaluating a fair game of chance, in order to be fair, okay, notice this is not your advantage, this is fair. So to be fair to both sides, the expected value should be 0, meaning everyone comes out the same. If you played this game 1,000 times, you would have the exact same money that you started with. 0 change. Okay? A positive value is a good thing. If there is a positive value, which, by the way, there is never a positive value in a casino, that means you have the upper hand. So if someone gives you a game of chance, you calculate the probabilities, and it comes out positive, you should just never end playing that game, because the more you play, the more you'll win. Okay? But that's never the case. A negative value, this is what casinos have. Your opponent has the advantage. Okay? Meaning they are more likely to win money. So let's test this random game of chance that I created myself. It is not anything real because there's not very many outcomes. It just makes it easier to deal with. Okay? So to be fair, it has to be 0. Okay? So be careful about that. A lot of people think positive is fair. No, positive is not fair. Fair means 0. Anything other than 0 is not fair. But positive is good for you because you have the upper hand. Negative is bad for you because your opponent has the upper hand. Okay? So if we look at this, all we need is the expected value, right? To evaluate game of chance, fair game of chance, you only need the expected value, which, by the way, I will underline that because it is the mean. I have the symbol there. I already told you earlier, but the expected value is the mean. So that's why I only have one column to fill out here. I don't need the variance and standard deviation. I just need the mean. So let's multiply this together. So we get negative 2.4, 0, and 1.8. Okay, so to find the mean, you take the sum of all of these. So the sum of x times p of x, right? Which is what we just have been doing. So I get a mean of negative 0.6. Okay, so now we have to actually use our answer. Is this a fair game? Nope, it's not 0. Explain. Your opponent has an advantage. Because it's negative. And there we go. We have evaluated whether it is a fair game of chance. Okay? So you have your 3-sentence summary.